So let's get a definition of current. You saw it in the video in the previous section that when we're talking about current, it's similar to what we did with fluid flow. So if we have a conductor and then we have some electrons that are moving through here, and we'll say the electrons are moving in this direction, which is counter to the conventional. Remember, conventional would be moving in this direction. That's the conventional charge. Anyway, as the electrons move through, what we do is we look at a little cross-sectional area, just like we did with fluids, and we want to see the amount of charges that are passing through here in a given time, and that's what we call current. So we use I for current, and it's just the amount of charge moving through a cross-sectional area over some given amount of time. And what you can see is that it's defined, if you think about this charge, our units are going to be charges in coulombs, and this is in seconds. So it's a coulomb per second, and we could say that one coulomb in 1 second, we define that to be 1 amp, or ampere, if you want to be cool like that. But we normally just say amp. So 1 amp is 1 coulomb per second. So you have 1 coulomb of charge passing through an area. And remember, a coulomb is quite a bit, and that's a lot of charge. So let's think about this. Let's just start looking at a problem. We have a 100 watt light bulb. So 100 watt bulb with a current of, let's say 0.83 amps. How much charge goes through the bulb in 1 minute? So we have a light bulb. Let's see. There's a light bulb. Looks like a skull. Okay. So we have a light bulb, and we're gonna have some current that's flowing through it. So we have some electrons coming in, heating up, passing through the filament, heating up the filament, and then passing out the other side. And that's determined, that's the 0.83 amps. And so the question is, how much charge? Well, we start with our current definition, which is the charge over time. And we can just arrange this. I want to solve for that. So we multiply on the other side. So my charge is going to be the current times the change in time. So we get 0.83 times the change in time, which was 1 minute, but we don't put 1 because it's in minutes. We put 60 seconds. And that would give me my charge, which would be, I think, 50 coulombs, since it's in charge. Okay, now we're going to talk about, we're going to change the subject just a little bit. It's still current, but let me get a new, or you know what, I may have room. Let's see. All right, let's see. No, let me get a new page open real quick. Open new. All right, so say we have some current. Let's just think of a river. Let's think of water. Again, this is why we did fluids at the beginning of the year. And let's say it breaks apart, so we get this juncture like this. And then it's going to come around, and then it's going to get back together. All right. So the question is, how does the current here, I'm going to use I, even though we're kind of talking about water here, how does that compare to this over here? So it comes in and then it goes out. So how is this current going to compare? Well, in fact, what we'll see is that I1 is going to be the same as I2, regardless of what happened in between. This is conservation of current. The current stays the same. However, you can see it's been split. It's been split, and we assume that the radius here is the same, so therefore we'd have the same. So we'd have like this I3 right here, and then this would be I3. And then it doesn't seem that difficult to then conclude that I3 plus I3 is going to be equal to I1. So I1 is going to be equal to I3 plus I3 because we have to have conservation of current. So it can split, but we're going to end up, it all adds up, okay? Now this is called Kirchhoff's junction rule. Kirchhoff's junction rule. Junction rule. And basically it says that the total current coming into a junction is equal to the total current going out. Yeah. So let's say that I had, I don't know, let's just make some stuff up. And then it comes back together like so. Doesn't matter about the shape. And let's say we had 5 amps moving on this side. So my current on this side is 5 amps. So then you know that this over here also has to be 5 amps. And then let's say this side is 3 amps. Then what's this one got to be? Well, since the 5 split and we know that the total in has to be equal to the total out, this part right here is the out part. This is the out. So we know that 3 plus this has to be equal to 5, so we know that it's going to be 2 amps. That's all that it says. That's Kirchhoff's junction rule. Let me show you another one. See if you can do this one. So let's think about a more complicated situation. Suppose that we had, I'm just going to draw lines, but you can imagine that these are here. I'll try to do it. Okay. So we have all these pipes that are feeding into this central area, and then we're going to have some current going in and out. Let's see if you can figure out what's going on here. All right, so let's say we had 3 amps going into it. Over here we could have, say, 6 amps coming out. Let's do 4 amps here going in. And we'll do 2 amps coming out. What's going on right here? How much and in or out? This was 4. All right, so we know it all has to be the same. So what we can do is we can just analyze what's going in, what's going out. Because the total charge or the total current in has to be equal to the total current out. So coming in, we have 3 amps plus 4 amps. And on the other side, we're going to have 6 amps plus 2 amps. So coming in, we see we have 7 amps. And going out, we have 8 amps. So it's clear we need another plus 1 amp going in. So this one needs to be 1 amp going in. And then we'll be good. That's Kirchhoff's junction. You know, there's other ways that you can analyze it, but I think the principle is pretty straightforward. But that's it.